Assalamualaikum and a very good day to our respected lecturer and friends. My name is Nozilawati binti Zukri and I will be the first presenter for this video. Okay, in this video, we will present the solution of a system of linear equation using the Gauss-Seidel and Jacobi methods, which are well known and iterative method in numerical analysis. Okay, first, let me briefly understand what a system of linear equation is. Okay, a system of linear equations consists of two or more linear equations that share the same variables such as x, y, and z. Okay, the main objective of solving such a system is to find the values of these variables that satisfy all equations simultaneously. Okay, in many cases, especially when the system is small, we can use direct methods such as Gaussian eliminations or metric inversions to obtain the solutions. However, when the system becomes large or more complex, this direct method can be computationally expensive, time-consuming, and sometimes inefficiently. Because of these limitations, iterative methods are often used. Okay, two commonly used iterative methods are the Jacobi methods and the Gauss-Seidel methods. Okay, these methods begin with an initial guess and then repeatedly improve the solution through successive iterations until the values converge to a stable and accurate result. The objective of this video are threefold. First, we will solve a system of linear equations using the Gauss-Seidel method by hand in order to clearly understand the computationally step involved. Okay, second, we will demonstrate the solution using Mathematica, which allows us to verify our manual calculation and efficiently obtain the numerical solutions. Finally, we will compare the Gauss-Seidel and Jacobi methods in terms of convergence, efficiency, and accuracy. Okay, this comparison will help us determine which method is more suitable for practical numerical computations. Okay, let us now consider the following system of linear equations. The system consists of three equations with three unknowns, namely x, y, and z. Before applying any iterative method, it is important to check whether the system satisfies the convergence conditions. Okay, in this case, the system is diagonally dominant. This means that in each equation, the absolute value of the coefficient on the diagonal is greater than the sum of the absolute value of the other coefficient in the same row. For example, in the first equations, the coefficient of x is 10, which is greater than the sum of the other coefficients. Similarly, the second and third equation also satisfy these conditions. Okay, diagonally dominance is important because it guarantees the convergence of both the Jacobi and Gauss-Seidel methods. Therefore, this system is suitable for solving using interactive methods. In the next part of the video, the following presenter will demonstrate the Gauss-Seidel method by hand calculations, starting from the rearrangements of the equations and the selection of initial guesses. Okay, with that, I will now hand over the explanation to the next presenter. That's all from me. Thank you.
Hello and a good day to everyone. So my name is Nuri Niwani Natasha binti Muhammad Rizwan. So in this video, I will show you guys how to solve a system linear of equation using two methods, which is Jacobi and Gauss-Seidel method. So
you can see here, we are given the equation is 10x minus y plus 2z equals to 6. And then the second equation is minus x plus 11y minus z equals to 25. And then the last equation is 2x minus y plus 10z equals to negative 11. And then as we can see, the system is diagonally dominant. And then it means both Jacobi and Gauss-Seidel will converge. Okay, next we rearrange each of the equation so that only one variable on the left hand side, like this: x, y, and also z. So this formula we will use repeatedly during the iteration process. Okay, the first method we use is Jacobi method. Okay, what you have to know is in Jacobi method, all new values are calculated using only old value from the previous iteration, and we do not use updated values immediately. And then as you can see here, I have already write the equation, and then when we substitute the x, y, and z, we will get like this. And then we will start our calculation by using the initial value, which is 0. So as we can see here, this is our first iteration, and I will substitute the values 0 here, also there, and we will get 0.6. For y, we will get 2.2727, and then for z, we will get negative 1 of 1.1. And then from the values first iteration, we will substitute into the second iteration, which is, as we can see here, I use this value, and also this one, and we will get the values of the second iteration. So for the next iteration, we will repeat the same process for the third iteration, fourth, fifth, sixth, and seventh. And after several iteration, we will get x is approximately to 1.04, y is approximate to 2.27, and z approximate to negative 1.08. And the table is given like this. And here we can see the value is already converged like this, and this one, and also this one. So for Jacobi method, we will get 7th iteration. Okay, we will move to our second method, which is Gauss-Seidel method. And what you have to know is the Gauss-Seidel method is quite similar to Jacobi method, but there is one important difference, which is the new values are used immediately once they are calculated. So this method usually makes Gauss-Seidel is faster than Jacobi to solve our problem. So as we can see here, the first thing is also the same. We have to rearrange the equation to let the only one variable on the left hand side, which is x, y, and also z. And then as we can see here, I also include the formula for Gauss-Seidel method. And then our first approximation is, we use 0, and then we will get 0.6, and then the value 0.6 immediately used in the calculation. As we can see, for y1 we include the 0.6 into it, and we will get this value. And then for z, we use 0.6, and then substitute immediately this value, and we will get the value of z1. So we will repeatedly use the same process for the second iteration, third iteration, and also the fourth iteration. And as we can see here, we will calculate until the fourth iteration, because we also get the value is converged. We will get x is approximate to 1.04, and y approximate to 2.27, and also z approximate to negative 1.08. This is the table. As you can see here, the values is already converged here and also here.
In summary, both Jacobi and Gauss-Seidel method can be used to solve the system of equation, but if we use Gauss-Seidel iteration, is more faster than Jacobi method. It is because Gauss-Seidel use the updated value to calculate the iteration, so it makes Gauss-Seidel is more faster than Jacobi. So that's all from me. Thank you for watching.
So, other than using hand calculation, we can also solve a system of a linear equation by using the Jacobi iteration method and Wolfram Mathematica. So this is how we solve it by using Wolfram Mathematica. So the first input A is the coefficient matrix for the system of a linear equation.
So the second input B is the constant vector of the right hand side of the equation. And the third input is x type, which is the initial guess, which provides the starting values of the iterations. So we have to press the shift enter, and then we obtain the output, which is an approximate solution vector. So next, this is how we solve the equation by using a Gauss-Seidel method in Mathematica. So this is the coding, and as we can see, the input here is, the first one is the coefficient of matrix A. The second input is a constant vector B, and then the initial guess is given by the vector X. And as we can see here, each variable is updated sequentially. This process is repeated for 10 iterations to get the accurate solution, which contains the approximate solution after 10 Gauss-Seidel iterations.
Next, I will compare the Gauss-Seidel method with the Jacobi method in terms of convergence, efficiency, and accuracy. Based on the results obtained from both the hand calculations and the solutions using Mathematica, we can clearly observe the differences between these two iterative methods. In terms of convergence, the Gauss-Seidel method generally converges faster than the Jacobi method. This is because the Gauss-Seidel method uses the most recently updated values immediately within the same iteration. In contrast, the Jacobi method relies solely on the values from the previous iteration when computing the new approximations. As a result, information is generated more quickly in the Gauss-Seidel method, allowing it to approach the exact solution in fewer iterations. Next, regarding efficiency, the Gauss-Seidel method is considered more efficient than the Jacobi method. Although both methods require a similar number of arithmetic operations in each iteration, the key difference lies in the total number of iterations needed to reach convergence. Since the Gauss-Seidel method converges more rapidly, it reduces the overall computational effort. Therefore, for large systems of linear equations, where computational cost and time are important considerations, the Gauss-Seidel method is generally more suitable and practical. Lastly, in terms of accuracy, both the Jacobi and Gauss-Seidel methods are capable of producing accurate solutions, provided that the convergence conditions are satisfied. When both methods converge, they tend to approach the same numerical solution. However, the Gauss-Seidel method achieves the desired level of accuracy in fewer iterations compared to the Jacobi method. This makes Gauss-Seidel more practical in real-world numerical computations, especially when high accuracy is required within a limited number of iterations. In conclusion, both the Jacobi and Gauss-Seidel methods are effective iterative techniques for solving systems of linear equations. However, based on our comparison, the Gauss-Seidel method is generally preferred because it converges faster, more efficient, and achieves accurate results with fewer iterations. Therefore, for most practical applications, especially those involving large systems, the Gauss-Seidel method is often the better choice. That's all from me. Thank you.